All right, then we directly jump into the next talk, which is my talk on reinforcement learning for a social distancing problem. I'm Arturs, a PhD student at SINTEF and the University of Oslo. Just as I get to rock many badges, so does this project. So on one hand, it's a project at SINTEF called Mathematicians Against COVID, with a goal of safely filling in public venues, seats in public venues under the current social distancing guidelines. But on the second hand, it's also a course project at the university in a reinforcement learning class. So the goal there was to explore a variety of reinforcement learning methods to solve this problem. And so I will introduce these methods today. And of course, this is a lightning talk, so many questions will be left unanswered. So feel free to reach out to me. So what is reinforcement learning? Well, this is probably the single one slide you will always see about reinforcement learning. It's about an agent learning to act in an environment by interacting with it. And kind of the key parts of this interaction are the state that the agent gets to observe and make actions based on this state. And the environment then gives the future next state and the reward. And of course, the agent then learns to act accordingly as to maximize the reward. So how does this problem look in our case? In the seat allocation case, well, our state is completely described by the auditorium, which consists of these fixed seats. These can either be empty, marked as the empty bubbles, or filled with people, or they can take the role of a buffer seat. So a buffer seat is necessary to ensure a distance between the groups. And the orange bubbles coming in, well, those are the different groups. And let's say in our case, we have groups of 2, 3, and 4 people coming in. And the agent, depending on this observation, then makes the decision on where to place these people. And also provides a reward. Right. So before we can jump into the methods, the different agents that can be used for this method, we need some kind of a reference to evaluate which agents, how well are these agents doing. So we establish some baselines. So if you would act randomly, there are in total 98 seats. If you would act without any plan, you would probably fill about 30 seats. If you were a bit more clever about it, and in each step, try to utilize the existing buffers as much as possible, not create any new ones, you will get to about 36. We call this a heuristic. And in like the best case, when only groups of 4 come, the optimum, it's 40. So we hope that our agent is about in this region from 36 to 40. Right, so then perhaps the most important concept in reinforcement learning is the notion of value. So the value just basically describes how much reward can I get out of the current situation until the end of my interaction. And we can write down these values both for states or state action pairs. And if we knew all these state action pairs, which we call the Q values, the problem would actually be solved, because in any given state, we would pick the action that has the largest Q value. But of course, we don't know them. We have to learn them. And this is where Q learning comes in, a very classic reinforcement learning method. And it is basically based on the Bellman equation. And here, this is like a simpler form of Bellman equation, which says the Q value of a given state and action consists of the immediate reward you get after performing this action in the state, plus the value of the state you land in. But of course, you don't know really in which state you will land in. So in this case, you could get any of the possible group sizes. So assuming you somehow, again, know these values, you can average them by the probability. And if you do that, you determine the Q of the state. Of course, you don't know the values of those next states, but the only thing you do know is the value of the terminal state, so the very last state, and that's 0. So you use this information to backpropagate it throughout all your possible states and actions. Right, so if you do this for, let's say, 100,000 steps, you get decent performance, but you don't quite outperform even the heuristic. So why is this? Basically, there's a huge number of states and actions to visit. So you somehow need a method that generalizes over multiple states and actions. So this is where neural networks come in, and a particular method utilizing these neural networks is that of the larger class of actor-critics. And as the name suggests, there are two key parts, the actor and the critic. Both are neural networks that you train. The job of the actor is to give to a given state, provide confidences about actions, which actions to take in this state. And the critic obviously just estimates the state value. And through like a clever interplay, you can train the actor and the critic to act in the environment. Right, if you do this, doesn't actually work that great in my case. Why is this? So the system is quite complicated with neural networks. You need a lot of training. And a particular problem I observed is that the critic never converges to like a really stable value. And this is because of the stochasticity in the environment, because of course you can never exactly know the value of a state because you have stochasticity. So my idea was a very intuitive one to model these uncertainties explicitly and build a tree search. But instead of using a naive tree search in which you expand all possible actions and you use the pre-trained actor you already have to expand only the most, the best actions basically, and kind of explore what happens in the next few steps. And then you can use this tree to backpropagate the values, and the leaf nodes you can evaluate using your critic. And again, you weight these values with the probabilities of them appearing, and when you take actions, you take the best, the action that leads to the largest value. Right, so in this case, it's the leftmost action, right? And this actually worked surprisingly well and increased the performance of the actor-critic system by like 1 seat filled on average. And it was the first method that actually outperformed the heuristic. And the most important thing I learned there was that planning was somehow extremely important, or at least helpful. But the issue with this kind of hacky approach is that the agents, the actor and the critic, still have to be trained using some kind of other method. So planning and learning are disjoint. So I started researching what could be done to use planning during learning, and this is basically what is done in AlphaGo or AlphaGo 0. And I modified the system to my problem. And the idea there is basically very similar, but instead of expanding all actions or the best actions, you kind of sample from action and you sample from the environment. That way, you don't get a large tree that you have to keep a track of, but only use samples from the tree. And then you use the information as tree to update your neural networks. So you go back and forth, and each improves each other. Right. But it turned out this, again, didn't work extremely well. It worked similar to the previous method. And again, I think the problem was that this system is hugely complex with a lot of moving parts, 2 neural networks, search tree, and it's very expensive to evaluate this tree or specifically these neural networks. And it turned out that if I turned off the neural networks, never asked for their opinion, never trained them, just did pure Monte-Carlo tree search, which allowed me to do a lot more iterations and tree search. It performed the best out of all methods. And so again, this reinforced the notion that planning is essential. And the fact that complex methods, although they offer a large potential, they are also finicky to get to work. And so with that, I thank you. And if there are any questions, please feel free to reach out to me.